This is the second part of this talk on locality and storage and memory. And Michelle Efros in her talk said that systems with memory are difficult to handle, and then also I favor, memoryless processes, and so I don't remember what I said last time, so let me begin from scratch, more or less. And I will not go through the motivation, but perhaps to remind ourselves codes with locality. And what we need, what we want is a block code over a finite field. And the additional feature on top of the textbook applications is that given a code word, a symbol in the encoding can be found, its value can be computed by reading off a small number of other symbols in the same code word. This number R is called the locality parameter. So if we lose the first coordinate in the encoding, we should be able to find the value of that coordinate by reading, let us say, some three symbols. Now these three symbols are called the recovering set of the first coordinate, and they are an element of the construction, and we showed an algebraic construction of codes with that functionality. And there is another line of work, and I'm mentioning this now because I was asked after the last talk. It seems that I didn't really stress the difference between the regenerating codes and codes with locality. Regenerating codes, they strive to accomplish a more powerful functionality, namely, we need to be able to recover the data in this MDS sort of way. We need to be able to access any, so many nodes. I don't remember the notation. I think it was not D, it was maybe K. So we need to be able to access any K nodes and read off the data. This functionality is not built into locality codes, so that's why locality is easier to accomplish. And the repair process has only one requirement, that we just restore the value of the lost coordinate. Right, and so that's the difference. So I'm not doing regenerating. There is an interesting set of problems, links with network coding and other similar questions, but I'm more on the locality side. Last time we constructed a family of Reed-Solomon-like codes that meet this new singleton bound by Gopalan and his co-authors. And one of the main distinguishing features of this construction was that the size of the alphabet is about the length of the code, which is a desired feature in these applications, as opposed to larger alphabets that may be useful in network coding and similar problems. But here they would stand in the way of possible implementations. So small alphabets are good here in this application, and this is what we did last time. And I will mention another bound, the asymptotic Gilbert-Parshall bound with locality. I'm mentioning this because I will use it later. So this is the upper bound, this is the lower bound, the existence bound. Perhaps I should put it on the board. What is R, what is delta? We start with the code C of length n. Let us say a linear code, so the dimension of C is k. Then we say the rate of the code, the relative distance, and we denote it by delta. And then we write A and D is the maximum cardinality of a code C. Distance of the code is D. We define the function R of delta as lim sup So in words, R of delta is the largest achievable rate in a family of codes as the block length goes to infinity, optimized over all possible families. We would like this to be the limit, but we don't know whether the limit exists. So we write lim sup. And then maybe locality R could be added. And then R is thought to be a constant. So R does not vary with the length, which seems again reasonable in these problems, because who would want locality that becomes large as the block length becomes large? That's not really locality, that's something else. And then there exist families of codes of rate at least R by R plus 1 minus the entropy of delta. Right, and the derivation is very similar to the classical GV bound. So Ritz-Solomon codes can be extended in two ways. And I'm saying this perhaps because perhaps I should first say why they should be extended. But, well, the order has been switched. So they can be extended to codes and algebraic curves, and then we can consider cyclic codes and BCH-like codes if needed, if we want codes over smaller alphabets. Let me motivate the need for these extensions. So let us look at the picture of algebraic codes that will be completely redundant for if you took a course on algebraic coding theory or encoding theory in general. This is not needed, but to be on the same page, let me just go briefly over that. So Ritz-Solomon codes, the length, we fix the alphabet. We start with a fixed alphabet. The length of the code is at most q minus 1. Well, this is not exactly true. It can be q plus 1, but never mind. Let's say q minus 1. The dimension, of course, is between 1 and n. The distance is n minus k plus 1. Right? So to construct the code, we take a set of points in the field, p1 through pn, n is the length. We take the message that we want to encode. The message consists of k symbols in the field. We make a polynomial out of that message. This is not fi, this is ai. That's a typo, sorry for that. But there are k coefficients in the polynomial, and these coefficients are the coefficients in the message. The degree of the polynomial is k minus 1 or less. And then we take the polynomial, evaluate at the p's, and that gives us the code word of the Ritz-Solomon code that corresponds to this message. Again, the fi's should be ai's. So by construction, of course, the length is less than q because we are taking q points in the field, and there are only q points. We are taking n points in the field, so at most there are q points, right? So the length is constrained. So that is the first obstacle, right, in the way of generality. What if we want larger length over the same field? Ritz-Solomon codes do not give us that, so we need something else. And a remark on the way, so the message space here, it can be thought of as the span of the family of the following family of functions: x to the I from 0 to k minus 1. Right? Is another representation of the space of message space. This span of functions, it will be again useful in what I'm going to say. So let me put this on the slide here. So what if we want more points? Oh yes, recall the MDS conjecture. What is the MDS conjecture? It is the fact that a code C is called MDS if the distance and the MDS conjecture says that the length of the MDS code is at most, well, to be precise, we need to have several cases, but roughly, let me say q. It can be q plus 1, it can be sometimes q plus 2, but no constructions are known of MDS codes of length larger than q plus 2. And the conjecture says that it is not possible. And not very recently in a series of breakthrough papers, it was proved in several cases by Simon Ball, and I think on occasion with co-author. So many cases of this conjecture are still open. But the MDS conjecture says not only Ritz-Solomon codes, you cannot have an MDS code of larger length in general. So then, what if we want longer codes? Well, then we need more p's. How do we increase the supply of p's? Well, we take curves. What is a curve? Well, it's not possible to say what is a curve, but what we can say that then P will have more than one coordinate, right? X, y, X, y, Z. And so that is the idea. So why is this so inspiring? Why do we really need to look in that direction? The reason is that in the standard error correction curves provided a suite of fascinating results in terms of code construction. So let us briefly look at those results to see that, well, this is a rather established area, those codes on curves, and let us see what they can provide. So the GV bound without locality, R over R plus 1 is replaced by 1 here, and this is the bound. We discussed the proof last time, and you probably know the proof. And even if you don't, it's pretty elementary, and there's nothing deep about this argument. All right, so then, at the same time, oh yes, so the GV bound for a long while had been the best known bound on the R of delta function, which we defined right there. And it depends on Q, of course, because the argument depends on Q on the size of the alphabet. And so if Q is 2, this is still the best known relation. And in fact, it is conjectured to be tight, even though we really don't have an idea of how to approach, either to improve it or to prove its tightness. Each of these questions seems to be really very difficult. And in classical coding theory, this is perhaps the most famous open problem about the tightness of the GV bound. But as we take Q to be larger than 2, let's say 3, 4, it's still tight. And then codes on curves give us something like this. And that came about in 1981 by Michael Fassman, Serge Bledutz, and Thomas Zink. And to see the relative quality of this bound, let us just plot it. Let's do the calculation. And I have this system offline, so I don't depend on the connection. And so I hope it will work. If I can find it, it should be here. Yes. So here I type the entropy. This is HQ. Let me make it nice, like this. Beautiful. Right. And then let me type the plot. Plot. What do I want to plot? 1 minus HQ delta, comma, 1 minus this Fassman-Bledutz bound, delta, minus 1, square root, Q, no, not that, minus 1, I need parentheses. So this is this Fassman-Bledutz. Let me plot this for all delta. Q minus 1 over Q. Why Q minus 1 over Q? Sorry, over Q. That's where the GV bound becomes 0. So codes of larger rate with a given relative distance do not exist. Now we need the value of Q, of course. Let us take Q to be something like 8. And well, the top bound here is the GV bound, and this is bound of codes from curves. It's not quite inspiring. So let us take 16 perhaps. 16. And it gets closer. And what is the next field? Maybe 27. But never mind. And also from this construction, Q needs to be a square. So we need a finite field, and then we need a square of that. So the next square is 25, but nothing good happens. After that, 36, but 6 is not a prime power. So the next is 7. And if we look at 7, then suddenly we see, it seems to be improving it, right? And we maybe can even enlarge it. And we see that it indeed improves it. So, and there is a poster about this, by the way, about extensions of this construction. But it is very tempting to plot this improvement as being much better. This is not the case really, but it improves it by a little bit. So it was a big result when it came about. Right? So it should show that GV bound is not tight for larger alphabets. And in fact, if we plot it for larger alphabets, let me make a movie out of that. animate that. How do you do that? Probably like this. Let's go q from 49, not that, 49. Let's take it to some large even power of a prime, such as 496. Well, it goes over all q's. Of course, it doesn't make sense. The codes do not exist over non-field alphas, but never mind. It still goes through the right points, and since this is continuous, this still gives us the picture, right? So let's see if this happens. So as you see, the improvement becomes bigger and bigger as the alphabet increases, and ultimately we improve almost everything except the corners. So yes, codes over curves are rather powerful. Let me stop this and go back to the slides. That's the motivation behind the construction. Before extending them to AG codes, oh yes, and those codes and curves, they're also called algebraic geometry codes because we need some algebraic geometry tools. And then algebraic geometry also abbreviated to AG, and so we speak of RS codes and AG codes all the time. So let us remind ourselves the construction of Reed-Solomon codes that we discussed last time. So the Reed-Solomon type codes, because this is now with locality. We start with a finite field that is fixed. Take a subset of points A as before, P1 through Pn. Let us say n is divisible by r plus 1, now where r is the locality parameter. Let us partition A into blocks of size r plus 1. Those are my recovering sets. If a coordinate in a recovering set is lost, r plus 1. So any coordinate here is lost. We read off all the other coordinates, interpolate a low degree polynomial of degree r minus 1, and then evaluate the polynomial at this pi and recover the lost coordinate. So let us partition into r plus 1 subsets. To encode the message, we have this double subscript aij, but altogether there are k symbols. So r times k, r times k over r gives us k symbols, and we have two subscripts. And similar to Reed-Solomon codes, we start with the message a, k symbols, this is my a. I make a polynomial fi. J goes from 0 to k over r. So here there is no typo, this is correct, fi. And then the typo was because of that. So now we make the polynomial fa, sum fi times x to the I. So this is the construction. And as a remark, the message space now can be thought of as, oh yes, what is g? G is a polynomial that made sense in this construction, g of x. So this is a1, this is a2, an by r plus 1. G of h is constant on each of the sets ai. It is easy to prove that set G exists. And it is also possible to construct it in some special cases where we can use the subgroups of the group of the field. And in fact, in the construction is rather flexible because this n doesn't have to be q. So I can start with q, with maybe q or q minus 1. But then maybe I don't need the last block. So let me just erase it. It still works. It's still an LRC code. And all the functionality is preserved. So I can have shorter length if I want. And an interesting remark is that now the message space is the span of the following functions. Previously we had just monomials. Now we have gxj, xi. That was the construction, and we have convinced ourselves, at least I convinced myself, that the recovery is done by polynomial interpolation. Right? So overall, this is called an evaluation code. We take the messages, we build the polynomials, we evaluate the polynomials at the points of the set A. Right? Evaluation codes. So then we look at this construction, and something is not natural here, at least to me. You see, it really bothered me for the whole year. This cannot be like that, right? What is this G? Constant on the subset, what does this mean? I don't know. Polynomials constant on subsets. Algebraically, that makes no sense to me. So, and then the Gx, Jxi, again, it doesn't look natural. I mean, why do we isolate this variable x? This is not true. It really should be Gy. But what is y? Right? So that question was really, really bothered me for the whole year, and I've been bothering Zach Tamon, my co-author, with this. And it hints of list decoding, by the way, and I still don't know if there is the link. If you know these new list decoding algorithms by Goswami and Sudan, then the picture is very similar. I don't know if there is a connection. It would be interesting to find it. That's by the way, one of the open questions I'm having in mind in regards to this construction. But never mind that. Let us try to interpret this G in some other way. So let us take an example. So let this be my set A, the set of points in F13, Y13 again, because we can do calculations by hand. No need in those primitive elements and things like that. Or rather, there are primitive elements, but we can do calculations modulo 13. So G of x, let's say it is simply x cubed. X cubed is constant on this set, and on this set. So the set of 9 points is partitioned into 3 sets of 3. So R there is 2 in this picture. N is 9. So therefore, G really maps FQ on FQ in the following way. Let us think about this mapping as follows. So it makes, out of x, it makes x cubed. And so we take some subset of points in FQ, map it on FQ, and let us think of those FQs as lines. What kind of lines? Well, let us even say they're projective lines. Yesterday, we mentioned projective planes, and then everybody agreed that that's a very familiar concept. And then maybe projective line is an even easier concept, right? We don't need a plane. So why do I want projective planes? Well, because when I move to curves, that becomes essential. Projective lines, it becomes essential, but never mind. So x maps the top line, I will denote it by x. On the bottom line, I denote it by y. It is not defined everywhere. It is defined on a subset A. Now, let me backtrack. It's defined everywhere, but I only need it on A for the moment. And what it does, it takes x, maps it on y in the following way. Above 1 on y, G of A1 is 1. There are 3 points, 1, 3, 9. Above 8, there are 3 points. Above 12, there are 3 points. And Marcelo told me that, if I had studied mathematics, I would call this a fibration. But, well, let's say this is a fibration. So above every point, there is a fiber of the mapping, and the preimage of every x in y consists of r plus 1, 3 points. So the function is constant on the fiber. We didn't say anything new. We just introduced a bunch of new words. But this is with an outlook for something to happen. Now, at this point, we should ask a geometer. And in my case, this was Serge Bledutz of the Fassmann-Bledutz inbound. I had asked many other people before that, but with Bledutz, it was better. And so he said, well, look, you map a line on a line. But what you should do, you should map a curve on a curve. and then things will happen. And why will they happen? Because curves are built in that way. Namely, if the curve is any good, then it is always possible to map it on some other curve, so that there is this vibration. Well, this is not a big deal, but what is important, that the points in the fiber will be contained in your finite field. That is a big thing in those curves, because it so happens they are defined over the algebraic closure. And there are always points, but if they're up there or in the extensions, we are not so interested. But what matters is that in curves, those fibers lie there where they call rational points. They lie in my field FQ. This is really amazing. So it turns out that curves are made for locality. So let's look at this curve, Hermitian curve. One wonders, well, the first question, if we haven't seen this before, why is this really a Hermitian curve? And what is this about? Practically, it is. So my FQ is F9, and I look at this equation, and if I ask the computer, and I did, and I already have this stored, so again, I don't need connection. So you ask this sage gap, you tell the gap, listen gap, I want this field F, I want the primitive element. Now I define a polynomial ring of two variables. So I introduce, the name for the variables, and then I have to say that the first variable is X, the second is Y. And then I introduce the equation, the polynomial, and then I ask, tell me what are the points on the curve. And it gives you the coordinates. So the first point is this. Z32 is a funny notation for the primitive element of F9. So it's alpha to the 6th and comma 0. And there are 27 points. Go back to the slides. And then alpha to the 6th is the first point I plotted here, and so on. Right, so it's very easy to do with gap. You don't need to do this by hand, even though, of course, it is possible. Let me see what happens after this. So why is this a Hermitian curve? Again, if this is new, let us generally we do this. We have the equation. We have Q0 square. In my case, 9 is 3 square. And then we write the equation. So we have projective coordinates x, y, z. What are those? Well, they count also for the points at infinity. And this z really counts for infinity. So if we substitute z equals to 1, then this is the affine plane, and z equals to 0 is the infinity, the horizon, the stuff at infinity. And the projective equation is this. So how is this Hermitian? Well, in FQ, exponentiation to the power Q0 is an analog of Hermitian conjugate. Right? It is this Frobenius automorphism that takes you through your conjugate points. And so we write this as follows. X plus y plus z is 0. And now, perhaps it makes sense to call it the Hermitian curve. And then from there, we substitute z equal to 1. So we forget about infinity because we don't need it in that construct. We need it, but it is kind of hidden. Never mind that. And we do a change of variables, and we arrive at that equation. So that's how this is a Hermitian curve. Very good. So in Ritz-Solomon codes, we had this space of functions, the monomials in the Ritz-Solomon type construction that we had g of x to the jx to the I. So those, and here we have this bunch of functions. I would not be able to say how these functions are found, but well, it makes sense to look at them. They form the basis of the space of functions, and now finally we know the meaning of y. So that is what y is. So we take the 27 points in this picture. We take polynomials now of two variables. We construct our evaluation code. So for instance, this is the message. This is the polynomial. And then we evaluate the first point is 0, 0. Substitute 0 for x, 0 for y, get 1, and that's my code block. That is my code block. Very good. So we have constructed Hermitian codes. What about locality? Well, it is clear now looking at these functions that if we project everything on y, then the projection accounts for a mapping that is constant on the fiber, right? And the value of the projection is 1. So it should work. I mean, we should have locally recoverable codes, and we do. Let us say this thing is erased, the point alpha 1. The recovering set consists of these 2 points, alpha 4, 1, alpha 3, 1. Interpolate a univariate polynomial. Why univariate? Because y is because y is fixed. Interpolate a polynomial in x. So we want f alpha 4, alpha 7, f alpha 3, alpha 3. Do a little calculation. This is f, and then substitute alpha. Alpha times alpha is alpha square, minus alpha square is 0, and so this is what we wanted to find. That's the way it works. Very good. Hermitian codes, let me run through this generality. This is what we have on the board. So the length of the code is now q to the power 1.5. So previously it was q, now it's on to q to the 1.5. So we get a square root q of the length. And there are other examples of curves. And then we get longer codes. So we obtain a family of codes with these parameters. Again, it would take me too long to really go over all of them, and probably this is really not the right occasion, because we need some technical details that would make this way too technical for this format. So interestingly, if we look at this picture, I always speak of projections down. What about projecting left? It seems kind of symmetric. So it should work that way too, right? Well, yes and no. There are points such that above them there is nothing if you look to the right. Yes, and this is called this phenomenon is called ramification. So the point is called totally ramified if the fiber consists of just that point. But well, I mean, nobody tells me that I have to take all the points. Let me throw out the ramified points, and then it becomes completely well, not completely. This is 3. This is 4 r plus 1. But I still can use this 4 for locality, and this works that direction as well. Right, and so we have, it is possible to project on x, and we obtain LRC code with locality q0. So what is restricting about that type of constructions? Well, this fibration, it has a fixed number of points in the fiber. And so locality is forced upon us. It is 3, it is small, it is good, it is small compared to the length, but we cannot really take it arbitrary. Well, all right, even in the Ritz-Solomon construction, we need some divisibility. So you cannot have really all of it. It's still a decent family of locally recoverable codes. We can, in fact, have 2 recovering sets for the point. So locality down is 2, locality left is 3. The length is 24 because I have deleted the 3 red points that do not fit my grand scheme of things. And it is possible to do more about this. And this is a part of this ongoing investigation. But the feeling is that it is possible to have codes with multiple recovering sets from curves in many ways. Well, generally, we take 2 curves, we project x on y. So I had x Hermitian curve, y was the projective line, I projected on the finite field. We choose a basis of functions. in this way. So the basis of the function space, and it is possible to convince oneself that we have a family of locally recoverable codes with a properly defined mapping under some assumptions. And
what's pi? What's pi?
Pi, well, the pi is projection on the projective line. So we take y, the bottom curve, and put it down to the projective line. And then we take it up, we take the infinity, we make a divisor out of that pi, and we take the Riemann-Roch space for the divisor. Now we want to beat the GV bound, right? Because no algebraic geometric construction is complete before we have improved the Gilbert-Warszawa bound. And there is this very good family of curves that are asymptotically optimal in a certain sense, the Garcia-Stichtenot curves. How do we do that? By the way, the Hermitian curves, they were plane curves. They were just two variables, right? So they were defined by one polynomial equation. Now, these curves are defined recursively. L, 2, 3, 4, 5, 6, 7, 8. And in every step, we add one more variable. So they are not plane curves. But they have many rational points. And if we do the calculation, then we have something like this Fassmann-Leduc bound. So previously, without locality, we had that. With locality, we have these two asymptotic bounds. We can project it two ways, right, as before. And they do improve the GV bound. So yes, this is somewhat satisfying. Although I should say that I don't think that the GV bound that I showed with locality is the correct GV bound. In the following sense, I think a better GV bound should be possible. And so I don't think that one is final. So I don't know how this improvement will fare once the right GV bound is derived. So for the moment, that's where it stands. It is better than this GV bound. So it's somewhat satisfying to understand this picture and to be able to improve asymptotics. So all of this appears in this recent little paper with Zach Tamo and Serge Leduc. Yes. Well, I don't know where we would be without Serge. Thanks to him. And you can find it there. And read the details if you're interested. But I should warn you that going down this route, it requires some background. Unlike other problems in coding information theory, where we really don't need to know much. We start with very simple tools and we still accomplish something. But here we need to know something. I mean, you cannot go around it, but some background is needed. So what next? Well, you take this book, for instance, by Dick Bleichut, and then you do this. Amazon tells you. But I should warn you, this is written in coding theory language. But he insists on Fourier transforms. And I don't know if that's the right way to approach this. You can do some things, but I don't know if this provides the needed machinery. And then you can take this, Oliver Pretzel. This is a nice book with examples and with algebra. And, well, maybe it still doesn't give you what you need. And then there is this serious textbook by Fassmann, Leduc, and Nogin. And I guess, well, if one wants to know more, there is no way around it. Right? What do you say? Well, all right. Let's go down to earth. Forget about algebraic curves.
Alex,
Yeah.
what did you achieve with those codes on towers?
On towers, asymptotically good families. So in this framework, we get codes with positive rate, positive relative distance, and fixed locality.
But maximum length for a given field size?
Maximum length for a given field size is infinity. $49, and then it can be anything. Because L grows without limit. So L can be infinite, and if L is infinite, we have infinitely many points. That's the whole point of this business, right? That we can, for a fixed alphabet, we can get very good codes of arbitrary length. That's in fact what Serge asked me when I approached him. I said, listen, I have this idea. And he said, and what do you want? I said, as always, I want infinite length. Cyclic codes, right? So why cyclic codes? Well, you start speaking about those large alphabets and Q this and that, 16, 49, 13. But then people walk up to you and say, all this good and well, but I want binary codes. I know that I can do simple things with binary codes. Can you have a construction? So there is a way to look at that from the perspective of the Ritz-Solomon codes. But before we go there, let me explain how this works in a more classical scenario. And again, this is the staple stuff from an algebraic coding theory class. But never mind, we're not in a rush, so let's go with this. So consider this Ritz-Solomon code. Length 15, dimension 4, F16, nothing fancy. So we evaluated at the points from 1 to alpha 14. This is all the non-zero elements of the finite field, and we get our code word. The message, let's say 4 symbols, this polynomial, and then we evaluate it at 1. And what does it mean to evaluate this polynomial at 1? Well, this means that we take the array of coefficients, take the dot product with the vector, with the yes, take the dot product with the vector 1, 1, 1, 1, evaluate it in F16, and get the first coordinate of the code word. Now we want to evaluate it at alpha. So we substitute alpha, alpha square, alpha 3. So it's the same as to take the vector of coefficients, compute the dot product with these alphas, get the value of the code word at alpha square. And overall, we realize that what we are doing, we are writing out the columns of the generator matrix. So this is the generator matrix of my Ritz-Solomon code. So let us remember that we can read off the rows of the generator matrix from the powers of the monomials in the polynomial. And it's the same picture. And it takes only a small step to figure out the parity matrix. The parity matrix is that, and you convince yourself that that's the case if you do the dot product of any row here and any row here. It is very easy to see that that is 0. And there are n minus k rows, so it should be a full parity matrix. And if that is the case, and C is a code word in this code, coordinates 1 to 15, let's write a polynomial. So multiplying by the row, this C, by the row of the parity matrix, now we go back from dot product to polynomial evaluation. So we are being told that C of alpha is 0, C of alpha square is 0, and so on, C of alpha 11 is 0. So the generating elements of the rows in H are the zeros of every code word. And since they're the zeros of the code word, we say they're the zeros of the code. So a cyclic code, this Ritz-Solomon code, why is this cyclic? Well, because indeed the cyclic shift of every code word is still a code word. So this code has zeros alpha through alpha 11. So that's another representation of cyclic codes that is really attached to this Ritz-Solomon picture. So what do we do next? We still want a binary code, maybe. Well, take this code C, and take this code RS code, call it the RS code, and take only those code words whose coordinates are 0 and 1. No other coordinates, so there is no alpha, no alpha square, only binary coordinates. This is a linear subcode because if we have two binary code words in F16, they add to a binary code word. So it is called the subfield subcode of the Ritz-Solomon code. And what is that? Well, they are called BCH codes. It is a binary cyclic code of length 2 to the m-1, and they're very important codes. They are mentioned in all textbooks. They are even mentioned in the modern coding theory textbook. So they are indeed very important. So this construction is called subfield subcode. And there are two observations to be made. First, we have this parity matrix, and we evaluate this in binary. And this amounts to the following. We take this alpha and expand it into a binary vector with 4 coordinates, because F16 is a 4-dimensional space over F2, so we can write 4 binary parity checks for each row here. And in that way we get a binary parity matrix. So that's one observation. And the other observation is that in binary, if alpha square is a 0, then automatically alpha to the 4 is a 0. Because in binary what happens raising to the power which is equal to the power of 2 is a linear operation. So we can take 2 inside. And then we have that alpha 4 is 0. And so we can delete the row with alpha 4. And so we have fewer parities. So we have greater dimension, but we expand this in binary. So then the dimension becomes smaller, and so there is this play with the dimension. So this is second observation, conjugate roots. Some parity checks become dependent. So generally, cyclic codes, right? Read Solomon code. The length divides q minus 1. Previously, it was any number less than q minus 1 or equal. Now I want divisibility because I want cyclic codes. Then we take the set of points 1 through alpha to the n minus 1, where alpha is the nth root of unity. We write the generator matrix, we write the parity matrix, we have the zeros of the code, the RS code, and we have subfield subcodes. So let us look at this example. What I would like to do now is the following. We have discussed cyclic codes. I want to construct cyclic codes with locality. In the next 2 or 3 slides, I will show a result that gives you a characterization of locally recoverable codes in terms of their zeros. I will tell you what we need to do, which zeros we need, so that the code is an LRC code. That is the next step, the step after that. So this will be done for its Solomon codes. The step after that will be, I will take binary codes. And I will see what kind of parameters we are getting. So in that way, we will get a large class of binary LRC codes. But before that, let us characterize cyclic codes, cyclic LRC codes in terms of their roots. Before doing that, let us again look at the following examples. So n is 15, k is 8, and then the distance is 8 because k plus d are n plus 1. Q is 2 to the 4. Let us say the code has the following zeros, alpha through alpha 7. It's a cyclic code, so the generator polynomial has all of those zeros, and the dimension is n minus the degree of g, which is 8. So I just plotted the zeros here so that we don't have to look at that. And we look at these triangles. In fact, these triangles could be placed anywhere on the line. It would still be a similar type code. And the BCH bound tells us that the distance is the number of consecutive zeros plus 1. It is very easy to understand why this is the case, because if we look at the parity matrix and the zeros are consecutive, then any submatrix will be a van der Monde matrix. And that will be non-singular. And the non-singular submatrices in the parity matrix translate into the minimum distance. The BCH bound. So now suppose we throw in some more zeros, namely this, with a step of 3, with the ultimate goal to have locality 2. So 3 is related to 2 by adding 1, and that will be general. So the claim is that we get the locality condition. And why is that the case? Well, then the polynomial. Remember I said that we can read off the polynomial from the zeros. And so that's what I'm doing. Is that what I'm doing? Not exactly, really. There is one light here, and the light is as follows. So we don't read off the polynomial from the zeros. We read it from the rows of the generator matrix. And so these are the parity matrix rows. So if we go back to the generator matrix, then we find this polynomial. So what happened with the dimension? It had been 8. Why is it now 6? Well, I added 2 zeros. I mean, 1, 4, and 7 are already here, but 10 and 13 are new. And so I have added 2 zeros. So I'm losing 2 in the dimension. So that is why the polynomial has only 6 coefficients. Now, I can read back the rows of the generator matrix from the polynomial. So the 1 alpha, alpha 3 alphas, 4, 6, 7, 5 is missing. And then I can read off the rows of the parity matrix. And well, we already know them, but again, they're as follows. So we take all the set of all exponents, we throw out these exponents, 0, 1, 3, 4, 6, 7, and then we take the reciprocals. And those are the rows of the parity matrix. So what's the dimension? Dimension is 6. I have added 2 zeros. And what's the distance? The distance is unchanged, right? The BCH bound is still in place. But when we remember this new singleton bound, we have to have something like this. So is it true that 8 is now n minus this new k, 3 divided by 2 plus 2? Well, yes, it is. So magic happens, it works. So by adding these 2 zeros, we moved from an RS code to an RS code with locality. So that's how we describe cyclic codes in the example. And let us have a theorem. So the main idea is this. We have 2 sets of zeros of the code. Consecutive zeros along the way of the BCH bound give us the distance. The jumpy zeros give us the locality. And you can see that we want as few zeros as possible because this boosts our dimensions. So we want the intersection of these two things as large as possible. And so we really want to start at the first and end at the last. And that's this divisibility that is forced upon us if we want this construction. So the cyclic code with zeros d and l has distance at least d plus 1 and locality r. And here is a theorem, a general theorem. It says that take a cyclic code over FQ, take consecutive zeros. Here are the consecutive. So distance, d for the distance, l for locality, and then we need jumps of r plus 1. So mod r plus 1, it doesn't have to be 0, it can be l, any l. And so these two sets give us a cyclic code with locality r, and this is singleton optimal. I'm not saying this is necessary, but this is certainly sufficient. So this describes a broad class of locally recoverable codes, right? And from there we can go down to BCH codes. Oh yes, before doing that, we are not doing anything particularly fancy because you know what is this locality after all? That's simply a parity check that we have in the code. If we recover a coordinate, so let me say this is the coordinate that is lost. And then we recover it by accessing this set, R coordinates. Well, this means that the code has a parity check of the following form. This is a row in the parity check matrix. Well, look at the parity check matrix. That's, of course, a code word in the dual code. And therefore, the dual distance is at most the locality. But for cyclic codes, it equals locality because I can rotate the code word with the minimum weight and I will get a local recovery condition for any coordinate I want. So for cyclic codes, the dual distance is equal locality. So after all, what we are doing, we are thinking of the dual distance of cyclic codes. So you would say it's a classical problem. What can we add there? Let me tell you what I can add. In the cyclic case, so the dual, what is the dual code, right? It's simply a code generated by the rows of the parity matrix. It's a set of vectors such that the dot product x c is 0 for every code vector in the code. Denote by d of c the distance of the dual code, or if we don't want to think of c dual, we simply call it the dual distance of the code itself. Locality equals dual distance.
What do you mean by locality equals dual distance?
I mean that r equals d dual. R plus 1 equals d dual. But I want to add one remark. Before I do that, let me speak about binary codes. So let us say we have one of those RS type codes with zeros alpha to alpha 4, alpha to alpha 13. So this is the distance part, this is the locality part. So let us take a binary code, the set of all code words whose coordinates are restricted to the binary field. A linear subcode, call it D. So D has all the zeros in Z and all the conjugates. So we can square it, and it is still a zero of the code. It is a subcode, so it has the locality that is at least as good as of the original code. In the original code, we could access any 3 coordinates to recover the value of the lost symbol. In the subcode, it is certainly still true. We still access any 3 coordinates. But maybe in the new code, we can get away with accessing 2 coordinates. So it may be by going to the binary code, we improve locality. The distance may go up, right? Because it is a subcode. So the distance of the new code is at least the distance of the original code, but it may be better. So by going from Reed-Solomon to binary, we improve it both ways. We increase the distance and we decrease locality. So it's really appealing to do that. But it cannot be as good. What is bad? Well, what is bad is that, of course, it is a subcode, so the dimension is smaller. So the dimension drops. But at least the other 2 features, they improve. So yes, what about binary codes? Oops. I'm sorry. Is that where I want to be? Yes. So the distance of the subcode is greater, the dual distance is smaller or equal, so the locality is smaller. It's a nice observation, and from that we construct some examples of locally recoverable codes. Binary locally recoverable codes. In fact, we construct a vast array of examples because I can now take any cyclic code, I can look at its zeros, I can arrange the zeros the way I need. And then I can take the BCH code of that kind and I get a locally recoverable code, binary locally recoverable code. It is not restricted to binary. I can take any Q, construct my Reed-Solomon code over Q to the M, such that 16 over to the 4. And then I take a subfield subcode to 16. And I still get a quote-unquote binary, now 16, what's the word, I don't know the adjective, 16 array code. So this subfield subcode construction is fairly general. And there are tools for analyzing this. The tools are very classical. Go back to the 70s. And they relate the behavior of subfield subcodes to the trace mapping from FQM to FQ. I will not be able to present the details, but the technique for analysis relies on what is called irreducible cyclic codes, minimal ideals in the range of polynomials. And we can make some conclusions about locality. And perhaps the best way to go is to show this table, which has a few examples. So how do you get that table? Well, first, you take a table of cyclic codes. And there are tons of them all over, right? And the first one is in the book by Peterson and Weldon in 1974. In the appendix, they have a table of all cyclic codes possible. There are not that many of them, perhaps a few hundred, maybe 1,000, of length up to 60. So you take any code out of there, you look at its dual code, and you see what happens with locality. And you compare it with your analysis. And if your analysis predicts the locality accurately, then you're happy. And those are the happy rows here. Well, length, dimension, distance, the zeros, the locality. There are more, I mean, cyclic codes, so we can rotate code words. So of course, there will be more than one recovering set. And this gives you the number of recovering sets per symbol. The zeros of the dual distance. Now compare these codes to upper bounds. This is the shortening bound, the Kadam-de bound. We can also run the standard linear programming bound for these codes. But the examples don't come close to these bounds. And they're so far off that in the last 2 rows I'm not even showing the bounds because it's embarrassing. So the question of upper bounds on codes with locality for small fields is very much open. I think it's a very valid open problem. Well, all of this appears in another paper with Zach and then Rob Calibank and his former student, who is now postdoc in San Diego, Sri Viparajan. There is a number of open problems. A few of them I have mentioned. Perhaps thinking somewhat more information theoretically, it is also of interest to study this. Study the trade-off between locality and gap to capacity. How does it constrain you? We know how it constrains us in terms of the distance and the rate. But what about if we run it on the channel? Do we want that for applications? Well, maybe to some extent. Maybe in the probabilistic setting of those disappearing nodes, it makes sense to look at the channel. Upper bounds have not been derived properly. So let me tell you what needs to be done here. We know the GV bound, let's say in binary. It looks like this. The rate and delta are related by this flipped entropy function. Well, what if delta is greater than 1/2? Then there are no codes, sequences of codes with positive rate, because there is also a Plotkin bound upper bound, or maybe if you are more used to network information theory, outer bound, and then the inner bound. And so the outer bound tells us that you cannot go beyond 1/2 in the distance without losing your positive rate. You can have a code of 0 rate with, let's say, the number of code words, which is n or 2n, but not more. But this picture has not been completed for codes with locality, because there is a gap. So with locality, I don't even know if I can plot it properly, but the gap is vast. So this point has not been established. Is there a relation with list decoding? Of what? Well, of this Reed-Solomon construction. And if there isn't an immediate relation with the known algorithms, then think of new algorithms of list decoding of these codes. Because there are many more questions, because what we did, we took classical coding theory, we threw in a new condition, and this new condition seems to have some contents to that. And so with that new condition, we can ask many questions from the textbook. They are valid problems. I started 10 minutes late, but I'm not going to go over the limit anyway. But I still have about 12 minutes. And in those 12 minutes, let me do this. In fact, in the abstract, I had promised something more. I said, well, I will speak of memory and storage. And this is storage, but what is memory? Well, of course, it's a huge topic. But my interest was in this rank modulation topic, which was mentioned here more than once. In the talk by Marcos, I remember he said something about flag manifolds being a generalization of the Kendall-Tau metric, even though I didn't understand that, but still it sounded related to rank modulation. And then yesterday, in the work from Estonia, it was also mentioned, was the central topic. So let me say a few words about this rank modulation. I promise to stop in 10 minutes. So let's forget about this algebraic construction, about cyclic codes, about locality. Let us consider something completely different, but still a coding theory problem. So now it's about memory. Not any memory, flash memory. Well, it all started with these works from Caltech when they said there is an alternative encoding of that is possible for flash memories. That was a few years ago, 6 or 7. So in flash memories, data is stored in cells, and each cell has few levels. In fact, this is not true. It has 2 levels, maybe 4, but I don't think it has more. It becomes very difficult, but for the purposes of analysis, let us say it has few levels. And over time, the charge begins to leak. They leak charge or leak resistance, depending on the technology. And then Q becomes Q minus 1, or 4 becomes 2, and so there are errors. And so Shuki-Brook and his students proposed to store, instead of absolute values, store relative values, store information in relative values of the cells. So this is the largest. Cell number 4 gets rank 1. This is second largest, third largest, and so on. And overall, we get a permutation. So information is now stored in the permutation on 7 elements. And now a coding problem arises, because what kind of errors, what can we say about those errors? So this rank modulation came, and then it led to extensions, to generalizations. We saw another metric. I will mention it a little later. And there are many more metrics. So let me say a few words about that. What kind of coding problems we see there. So let's formalize this coding in permutations. Before even doing that, let's say what is the elementary error? What is the generating element of the error space? Well, let us say this thing starts to leak charge. It goes down, 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 and at some point it oversteps its neighbor. So then 3 and 2 swap. So in the permutation, there is a transposition of 2 adjacent symbols. So the error space is generated by adjacent transpositions. Right? Elementary error, transpositions of adjacent symbols. This is a permutation written in full. 1 goes into 1, 2 into 3, 3 into 4. So in general, sigma 1, sigma n. And so we only write the bottom row and omit the top row. And then what we see here is a permutation from the previous slide. And then the error is adjacent transposition in that permutation. 6 and 4 have been swapped. 4 had been rank 1 and 6 rank 2. But after the error, they have swapped their positions. This is a general transposition. This is an adjacent transposition, and we are interested in the bottom row here. Permutations, of course, form a group, the symmetric group, multiply. We can take an inverse of this permutation will be that permutation, and we get the identity permutation. Identity permutation does not compute anything. Codes and permutations were studied even 40 years ago, maybe 35, starting at least with this paper, but there was stuff even before that. And then there were more. In fact, there were many more. I only gave a sampling of here. Ulam distance, this is a mistake. It should be n minus the longest increasing subsequence. That comes from this recent paper by Farjad Farnoud, Vitaly Skachik, and Olga Milankovich. So n minus the longest increasing subsequence, the Ulam distance. and which is an extension of these adjacent transpositions.
Your definition of the Hamming distance.
The Hamming distance is the number of different locations.
Yes, I'm saying where you have tau and the other side.
No tau, this is pi, I'm sorry again. It was done a bit in a rush, but I apologize. So this pi is the same as tau. The Chebyshev distance is the infinity metric on those permutations, and it has also been tied to rank modulation. And then the Kendall tau is, oh, I see, I inserted n minus in the wrong place. Yeah, sorry, it was about 2:30 in the morning. So n minus should be here. So the minimum number of adjacent transpositions. This is the Kendall tau distance. Forget about this. There are many other metrics. There is a whole survey by Desarman, metrics on permutations. You can find dozens of them. And you can study coding for each of them if you want. So what can we say about the number of adjacent transpositions? One interesting observation that the largest number is not n. In fact, it is n choose 2. To go from this to this, we need 6 adjacent transpositions, not 2. So the maximum distance now grows as n squared, roughly, not as n. That changes. If you go to asymptotics, changes the business. We can consider the weight or right invariance. So we can multiply by any sigma on the right, and then the distance does not change. It is not left invariant, though, which makes it somewhat inconvenient to operate with. But at least with the right invariance, we can think of the weight of distance to the identity permutation. So at least it makes sense to study spheres around 0 in the group. Well, let us ask ourselves, the array of standard questions. What is the largest possible size of the code with a given distance, and can we construct these codes? And this question turns out to be much easier than the same question with Hamming space. Namely, we can answer both questions, we can find asymptotically the maximum size, and we can construct good codes, in particular the codes that get there, with simple decoding. So this problem indeed is much easier. And there is one reason that the problem is much easier is this. So what is our alphabet? Well, first perhaps let us define the rate of the code. We take log of the cardinality. And previously we divided it by n. But what is n in the Hamming space? Previously, the rate is log cardinality divided by n. But what is n? Well, n is the number of bits that the channel that the entire code word can carry. So let me write it like this. Log c divided by log of the entire Hamming space. The size of the Hamming space, 2 to the n. And then we get log c divided by n. So in this case, we do the same thing. The total number of permutations is n factorial, and we take its logarithm. And so that is the rate. And call this capacity of rank modulation codes. The tools to work with these permutations in the Kendall distance are very much related to inversion vectors. The inversion vectors, it is a way of, so an inversion is this. 2 is out of order. 2 is on the left of 1 of the permutation. So it has jumped the queue. And we say that 2 is in inversion. And then from a permutation, we can write an inversion vector. It is perhaps the last thing that I'm going to define. So the inversion vector is this. How many inversions does 1 enter? Well, 1 cannot enter any inversions because it is smaller than everything else. 2 enters 1 inversion. 2 is on the left on 1. So in the second position, we write 2, 3. But everything to the right of 3 is greater than 3. So 3 enters 0 inversions. 4 is in 1 inversion to the right of 3, and so on. And interestingly, given an inversion vector, we can recover the permutation. Working from the right, it is easy to convince yourself that this mapping is injected. So we move to inversion vectors, and in inversion vectors we can work with L1 distance. It turns out that this mapping is in fact weight preserve, distance preserve. It's not distance preserving. This is not true. It's distance increasing. So working with the L1 vectors, L1 metric on inversion vectors, we can in fact find the capacitor rank modulation exactly. And it happens to be like this. So if the distance is n or below or proportional to n, then the capacity is basically 1. If it is proportional to n squared, it is 0. And if the distance is between n and n squared, 1 plus epsilon, then the capacity is 1 minus epsilon. This should not be surprising because we have our code alphabet is the same as the code length. But for large alphabets, asymptotic answers become easy. Even the GV bound approaches the singleton bound, as we saw in that animation. So we should expect that the asymptotic answer is easy to find, and it is not difficult to do so. And we can have constructions, rather explicit, from existing codes through inversion vectors, through some transformations involving the gray map. We can get to actually from pretty much any error correcting code, we can construct a rank modulation code. And if we choose them carefully, those error correcting codes in the Hamming space, then we can get to capacity achieving codes. And with simple decoding algorithms which rely on the decoding algorithms in the Hamming space. And so this was done a few years ago with ARIA. And on one occasion with Gilles. And that's where I end. Thank you.